It's kind of wild to think about. We learn about electrons, right? Tiny particles buzzing around atoms.
Standard stuff?
But try to actually picture one, like trying to grab smoke or something. Fuzzy.
Well, yeah. Indistinct is a good word for it.
But what if I told you that scientists have actually found a way to see the shape of this tiny thing, even when it's moving?
That's the really groundbreaking part here because, our understanding, it's mostly been these mathematical things, wave functions.
Or those abstract descriptions.
Exactly. They work, they're useful, but they're math in these weird multi-dimensional spaces.
Not something you can easily visualize.
Not at all.
Yeah.
So for the first time, we're kind of moving past just the math to actually measure a real physical property, the form it takes as it zips around.
And this isn't just, ticking a box for physics nerds, right?
No, not at all.
The report we looked at from Sustainability Times, it really stressed this isn't just theory. It's got potentially huge implications for tech.
Yeah.
For electronics manufacturing.
Absolutely. Think about architecture. Knowing a building shape, its structure, tells you how it works, how stable it is.
Okay, yeah.
It's sort of similar here. Knowing the shape in a quantum sense of a moving electron gives us this really fundamental insight how they act inside different materials.
And this Minggu Kang, who the report mentioned, was key at MIT and Cornell.
A pivotal researcher, yeah. Really push things forward. Their work could genuinely shift how we view materials at that basic level.
It's funny, the article also mentioned the pandemic, which sounds weird. How did that help?
Well, it's a bit counterintuitive, isn't it? But the shift to remote work, it actually helped connect people, experts all over the world.
So forced collaboration, almost.
In a way, theorists and experimentalists, maybe in different countries, found new ways to share data, bounce ideas around because they had to work remotely.
Huh. A strange silver lining.
It really highlights how modern science works sometimes. It's very collaborative. This project needed lots of different expertise, and the remote setup, well, it facilitated that international effort. Led by Ricardo Comen at MIT, by the way.
Okay, so the big question. Measuring the shape of something that small, and it's moving, how on earth do you even start?
Right. That's where this really cool technique comes in. It's called angle-resolved photoemission spectroscopy. ARPES, for short.
ARPES. Okay. Catchy. What does it do?
Well, imagine you shine a very specific type of light, like a precisely aimed beam, onto your material sample. When that light hits, it basically kicks electrons out of the material. It gives them enough energy to escape.
Like knocking marbles off a table.
Sort of, yeah. And ARPES is incredibly good at measuring exactly where those ejected electrons go, their angles, their energies, even their spin, which is a quantum property.
Okay, so you're analyzing the spray pattern, basically, the electrons flying off.
Pretty much.
But how does that tell you about the electron's shape inside the material before it got kicked out?
Good question. Think of it like maybe throwing different kinds of balls at some hidden complex object behind a screen.
Okay.
By watching really carefully how those balls bounce back, their angle, their speed, maybe how they're spinning, you can start figuring out the shape and contours of the hidden thing.
Right, you deduce the shape from the rebound.
Exactly. ARPES does something similar with light and electrons. It gives us this incredibly detailed picture of the electron state within the material, what we call their quantum geometry.
Quantum geometry. Okay, that definitely sounds more complicated than high school triangles and squares.
It is, yeah. Regular geometry, that's about shapes in our everyday 3D world.
Right.
Quantum geometry describes something more subtle. It's about how electrons are organized at the quantum level inside a material. Their energy relationships, their interactions, how their wave functions kind of twist and turn in relation to each other.
So it's not just where they are, but how they're connected and interacting.
Precisely. And this geometry, it turns out, massively influences a material's properties, like whether it can conduct electricity, perfectly superconductivity. That's often linked to quantum geometry.
And the report mentioned Kagome metals. Why them specifically?
Kagome metals are fascinating. They have this really cool atomic structure. It looks like a traditional Japanese woven basket pattern Kagome. Interlocking triangles.
Oh, interesting.
Yeah, and that specific lattice structure, it forces the electrons inside to behave in really unusual ways. You get these exotic electronic effects that are directly tied to this quantum geometry.
So they're like a perfect test case.
Exactly. ARPs let the researchers get this amazing, unprecedented view of that intricate electron bands happening within that specific Kagome structure.
Okay, so we can now effectively see this quantum shape, this geometry, for moving electrons.
Well,
What's the big payoff then? What does this let us do?
Well, this is where it gets really exciting for future tech. Understanding this electronic geometry, it's like getting the fundamental blueprints
Blueprints for what?
for designing totally new materials, materials where you can actually engineer their electronic properties very precisely.
So creating materials to do specific jobs.
Exactly. Imagine making materials that conduct electricity way more efficiently with almost zero energy loss, or materials with completely novel magnetic properties or optical properties.
The article did hint at things like, yeah, more efficient devices, maybe even boosts for quantum computing.
For sure. Those are definitely potential applications. Controlling electron flow and interactions at these tiny scales is key for so many future technologies.
It really feels like maybe the start of something big in material science.
I think so. Ricardo Coman, the lead researcher, had a great quote in the report. He said something like, "We have essentially crafted a blueprint to obtain entirely new information that was previously inaccessible."
Wow. Inaccessible information.
Yeah, it's not just about improving what we have, it's about potentially creating whole new classes of materials, things we maybe haven't even thought of yet, with functions we can barely imagine.
It really is mind-bending stuff, probing the actual shape of an electron as it moves. This deep dive, looking at that Sustainability Times report, it's definitely opened my eyes. A breakthrough that hits fundamental physics and future tech.
It really is, and it's a great example of, human curiosity pushing boundaries.
Yeah.
Developing these incredibly sophisticated tools like ARPs lets us ask and answer questions we couldn't even frame before, opening new doors in material science, quantum physics.
So I guess the big question hanging there now is, what comes next? What amazing innovations are we going to see emerge from actually being able to see and understand this quantum geometry?
That is the exciting question, isn't it? It makes you wonder about the fundamental nature of matter and what kinds of materials with, well, currently unbelievable properties might be possible down the line.
Definitely something to watch. Well, we hope this deep dive has helped shed some light on this pretty amazing breakthrough for you.
Hope so.
If you enjoy digging into the quantum world with us, please do like and subscribe. We do more deep dives into science and the world around us.
And we genuinely love to hear from you. What topics are you curious about? Let us know in the comments below. We do look at those.
Absolutely. Stay tuned for future discussions, and do check out the show notes. We'll put links there to related stuff and maybe some affiliate opportunities that help support the show if that's something you're interested in. Keep exploring, keep asking questions, and we'll catch you next time for another deep dive.